Alright, so now we are again going on with Kirchhoffs laws. Another important one is Kirchhoffs' second law. So we talked about the first or the current one previously. Now we'll be talking about Kirchhoff's second or voltage law. And Kirchhoff's second or voltage law, it basically says this. So in a closed loop, again, so just as we said that for Kirchhoff's first law, that was for a junction, so that was there was 1 mark for that. So similarly here you need to say in a closed loop for that 1 mark. You say this, that the sum of EMFs equals the sum of potential differences. And by the way, in your circuit, if instead of the electromotive force, if you write EMF, that's fine. If instead of potential difference, you write PD, in a theory part where you have to write this down, that's also fine, because these are abbreviations that the examiner knows and accepts. So sum of EMFs equals the sum of potential differences. Okay. So the idea is basically that, and we'll also be studying this in the context of series and parallel circuits later. Let's make a simple circuit here. So let's say it's a very straightforward circuit where you have a resistor and 2 EMF sources. Let's say that the voltage dropped across each one is V1 and V2 like this. This is the EMF. So a very simple example. So basically the EMF E is equal to V1 plus V2 because this is the loop that I have. So the EMF equals to the voltage V1 plus the other voltage V2. Also, this one, just as the other one was linked to the conservation of charge, this is a consequence of conservation of energy. All right, so that's the idea here. Now, why is this linked to the conservation of energy? Because we've previously studied what EMFs and potential differences mean. So let's say if you're talking about charge, a charge gains energy when it goes through the circuit. So that EMF, for example, if it's 9 volt, so we know that this means that for 1 coulomb of charge, 9 joules is given to it, and that energy is then lost across the resistors as potential drops. So that's the idea. It's basically just conservation of energy. Now, a very common type of question that we do have here is linked to KCL and KVL loop equations. So right into the mix with difficult questions. It's not been asked like in the recent past papers for quite some time, but it is part of the syllabus and you must know how to do this. So how do we write KCL and KVL loop equations? Well, there are just 2 rules apart from the statements that you've seen. The first rule is that if current enters the negative terminal of a cell, take that cell's EMF as positive and vice versa. So when we'll actually start doing the questions, you'll know why this is so, but this is the rule. And hopefully when we start doing the questions, you'll also actually know why this is or what's the reasoning behind this. And the other rule is this, that for example, sometimes you'll be writing loop equations, and sometimes what would happen is that the currents and how they're labeled in the question, they'll have clashing directions. So if currents are in clashing directions choose any one and what does that mean for the other current is that the potential drops due to the other current will be taken as negative. Let's look at this in the context of an example that I have, and it's a very comprehensive example, and once you do this, past paper questions will become a walk in the park. So this is the question, and using KCL and KVL, the Kirchhoffs current and voltage laws, you have to write down expressions. So the currents are labeled, EMF sources are labeled, and now we have to do this question. So first it says write down an equation for I1, I2 and I3. So we need an equation that links all of these. So I can see this junction where all of these are basically interacting. So I1 comes in, I2 comes in, I3 goes out. So I can then write an equation for part A really easily. So I can say that in part A, I can say I1 plus I2, sum of currents entering equals sum of currents leaving, which is I3. Part B, loop A, B, E, F, A. So this is A, B, E, F, and A. So there's two currents here, their direction is not clashing. So all I would do here is I can say these are going in the same direction. I don't need to go to rule 2. I can see that these currents are entering into the negative terminal of E1. I'm going to take this as positive, and entering into the positive terminal of E2. I'm going to take this as negative. Now let me also talk about what's the reason behind this. We know that conventional current flows from positive to negative. So if a current enters into the negative terminal and it exits out of the positive terminal, so we say this is how the current is flowing. But for E2, this is actually acting opposite to however E1 is, right? It's trying to make current flow in this direction. That's why we're taking this as negative, this as positive, and that's what you also just saw with the currents. So I'm using the KVL expression. So sum of EMFs equals sum of potential differences. So E1 minus E2 is the sum of EMFs equals the sum of potential differences. So the current, so I see two resistors, there would be potential drops across these. So this is going to become I1R because the current through this and this would be the same. This is a series circuit, so it's I1R plus for this one it's I3R. So I1R plus I3R, or I can also write it like this, factoring out the R, and it's I1 plus I3R. Let's look at part C now. Let me shift this here. Part C says loop B, C, D, E, B. B, C, D, E, B. In this case as well, I2 and I3 are in the same direction, so there is no clash. I don't need to do anything other than just see that which EMF is going to be taken as positive, which one is going to be taken as negative. Current enters into the positive in this one, this is going to be taken as negative. Current enters into the negative terminal here, this is going to be taken as positive. So I'll write E3 minus E2. That's the EMF part. Now the potential differences part, that is equal to the sum of PDs. So through this again I2 flows, so this becomes I2R plus I2R, so that's 2I2R plus I3R. So how I would write it again after factoring out the R is 2I2 plus I3R. What about part D? So loop A, B, C, D, E, F, A. A, B, C, D, E, F, A. Now I won't be talking about this, I'll be looking at all of this. Now in this case I can see that the directions of I1 and I2 are clashing. For no particular reason, let's take I1 as my reference. I could have also done it the other way and it makes absolutely no difference. So I1, if I look at this, so this is entering into the negative terminal of this one. This is going to be taken as a positive EMF, and it enters into the positive of this one, so it's going to be taken as a negative EMF. So I'm going to write E1 minus E3 here. this is going to be equal to the sum of potential drops. So in this case, the drops are here, here, and here. So this would become I1R, and this would become I2R and I2R. But because I'm going opposite to the direction of I2, I would take this as minus 2I2R, right? So it would become I1R minus 2I2R. So I1 minus 2I2R. Now some of you might be thinking, how would my answer be different if I took I2 as my reference? Let's look at the diagram. Then according to this, E1 would be negative, E3 would be positive. So it would be E3 minus E1, and then it would be 2I2R and minus I1R. Guess what? It's just this same equation multiplied by a negative sign. So it's completely flipped on the left and right hand side. That would also be entirely correct. So now you also know how to write the Kirchhoffs loop equations using KCL and KVL. You just need to keep these rules in mind.